Hello everyone, I am Ifat Jahangir, and today I am going to present our work on dual channel microcantilever heaters for selective detection of and quantification of a generic mixture of volatile organic compounds. So what are volatile organic compounds? So these are ubiquitous in our indoor and outdoor air. They are responsible for various health problems like eye, nose and throat irritation, headaches, loss of coordination, nausea, and they can also cause damage to liver, kidney, and central nervous system, and they can cause cancer, mutation, and birth defects. So there are different detection techniques already available in the market. They include integrated indoor air pollution monitoring and testing systems, heartbeat pelisters, and photoionization detector, to name a few. The main problem with these techniques is they are either bulky, expensive, they might have slow response, and also they often consume high power. And the most common problem is lack of selectivity with many of these sensors. So that's why we came up with a different idea of dealing with this problem. So here is the outline of my presentation. I'll first discuss the motivation of why we're doing it the way we do it. Then we talk about the device geometry and sensing setup. Then I show some results for selective detection of VOCs using one type of cantilever named as MDC-MH. Then I'll also show how we do analysis of a mixture of VOCs, and then how we also estimate the concentration of each constituent of a mixture, and then I will conclude my presentation. So here we are using 3,5 nitride based microheaters. So why are we using that? The reason is algan-GAN heterostructure that has strong polarization at the surface. So that aids in sensing vapors by enhancing surface interaction. They are wide bandgap material, so they are more immune to noise, and they are also chemically inert. And they are also stable at high temperature because we are building a heater, so we want it to survive high temperature. And we are using cantilever heaters because suspended structures have lower thermal loss, so that's why they are efficient in localized heating. Also, they are applicable in scanning thermal microscopy and conductivity based sensing. So there are some other modes of sensing that we can study with the same cantilevers. And most importantly, they are compatible with other MEMS based sensors. So here is the geometry of our sensor. So the first two pictures show the dual channel cantilever. So you can see there is one channel and there is another channel, and they are all sitting on the same cantilever. That's why we are calling it monolithic tip dual channel microcantilever heater. And there is a second type where we can see that there is a small air gap in between two channels. So we are calling it split tip dual channel microcantilever heater. And they are pretty small. The length of each arm is about 130 micron, and the base width is about 30 micron here, and the tip width is only 4 micron with a thickness of 700 nanometers. And here is our VOC sensing setup. So it's a test case. So we have two channels. From one we are just flowing high purity nitrogen, and the other one we are using a bubbler to create vapors of volatile organic compounds. Then we are mixing them and flowing them into the channel. So and we control the duty cycle of these two valves to get different concentration of the analyte. So here is our first result. So what we have, we are using 500 ppm of trichloromethane, and this is the baseline when there is no analyte. So when we start flowing gas, it starts going up and it shows a change of about 2.2%, and then it comes back down. And the rise time and fall time is about in order of 10 seconds. It normally goes up with low concentration, and at high concentration we can detect it within 5 to 6 seconds. And since we have two channels, I'll just go back here. So this channel is called the heater channel. So we are applying a high bias here, so it heats up. And this is the second channel, that is the sensor channel. It actually detects the sensor by using a heat transfer that we will discuss later. So with the heater channel, we can see that as we introduce the gas, the analyte, for the self-heating mode, that is the heater channel, after a certain bias, suddenly we start to see some change in current. And for the second channel, that is the sensor channel, we also see a response the same way. So in self-heating mode, we are basically having a Joule heating at the heater channel, and secondary heating mode, we are basically having the heater channel transferring heat to the sensor channel that does the sensing. And both heating modes are correlated with the bias of the heater channel. So here is the interesting part. So we found a correlation with the threshold voltage, that is this voltage shown in the green circle, the particular voltage at which we start to see the change, that is called the threshold voltage. So for these two different channels, the self-heating mode is from heater channel and the secondary heating mode is from the sensor channel. We see that these threshold voltages correlate with the latent heat of vaporization. I will explain it later why this is the case. And there is a table that shows all these data points, and that is also available in the paper. So this is the possible reason for this happening. So we have the device here that is causing Joule heating, and the analytes, since they are volatile, they are liquid in room temperature, they start to conglomerate in the air and they take heat from the tip of the cantilever, showing reducing the tip temperature. And since we have a polar surface, most of the normally volatile organic compounds are polar in nature, so they actually come here and interact with the tip, and they also take heat from the surface, which reduces the temperature and increases the current. And here we see the detection limit. So since as the concentration goes down, this response will also go down. So the challenge would be to how low this response can go until we can measure it. So at the threshold, since detecting the threshold voltage is the most important part, we are defining a threshold response, that is the response that we are seeing at the threshold voltage, and we are plotting it here for 4 different analytes as a function of concentration. And here we can see that extrapolating these curves, these points, we can actually detect up to down to 1 ppm, and the smallest response is observed just about here. Yeah, so that is the reason. And this is where we do the mixture analysis of multiple VOCs present at once. So when we have several VOCs present in the mixture, we just see a curve that looks like this for a self-heating mode, and for secondary heating mode is also like that. So we cannot really tell the difference whether there is one analyte or more than one. So what we do is we take the first derivative that also doesn't reveal much. So we take the second derivative of this curve that shows some peaks. Now we found out that each of these peaks correspond to the threshold voltage of that analyte, which also correlates with the latent heat of evaporation. Now with self-heating mode, since the peaks are so close to each other, it's very hard to distinguish them. But with secondary heating mode, you can see, if you look at the voltage scale, here within 3.5 volt we have all the peaks, but in the secondary heating mode all the peaks are spanned out within a space of about 4 or 5 volt. So we can separately detect all the small peaks. For example, 2-propanol and ethanol, these peaks we can clearly identify here, but with self-heating mode they are almost merged with each other. And also with concentration, threshold voltage also shifts, and that's why we need to know how reliable this metric is. So we see that at high concentration there is not much change, but as concentration goes down there is a shift in about 0.12 volt, which is not much, and we can reliably detect the VOCs. And this is the second type of cantilever that we have, that is the split tip cantilever. So here the primary mode, the self-heating mode is almost the same, but the secondary heating mode shows a response. If we take the first derivative of the response, we get 2 peaks instead of 1. So in the MDC image we get just 1 peak, but in SDC image we get 2 peaks. And when we take the ratio of these 2 peaks, we can actually estimate the concentration, because we can see there is a linear correlation. And so that is the summary of my presentation. So we have demonstrated a MEMS compatible heterostructure based dual channel microcantilever heater, which has a fast response time that is less than 15 seconds, and it can also detect VOCs with a low power consumption less than 3 milliwatt. A lower detection limit of 1 ppm has been established, and we can also detect the concentration up to for down to 40 ppm, and we can also detect multiple analytes simultaneously, and also we can detect them individually and also their concentration, and they are operable within a large range of concentrations from 1 ppm to 1%. Thank you.